All right, everyone, welcome to example 1, everyone's favorite. It's a word problem. So what we have is the sum of a whole number and twice its reciprocal is 73/6. We're going to set up an equation from that. So we know that sum means add. A whole number means it's not going to be a decimal. Twice its reciprocal. So let's go ahead and just call x our whole number. And if we're going to take the sum, that means we're going to add to it. So a whole number and twice its reciprocal. Well, the reciprocal of x would be just 1 over x. Twice its reciprocal means we will multiply it by 2. And then is 73/6. That sets up our equation. So as you can see, it's a rational equation. We have variable, we have fractions, I guess, within there. We've got a variable in the denominator of one of ours. When we go to solve this, there are a couple different things we can do. I'm going to first start by rewriting this way. Just kind of combining that 2, we can think of that 2 over 1 and multiplying straight across. And then what I'm going to do, and what will be common to the next couple problems we look at as well, is take this entire equation and I'm going to multiply everything through by all of the denominators to clear the fractions. So when I look at my first one, I just have kind of x over 1, and we know multiplying through by 1 isn't going to do anything. Then when I look at my second fraction, I have x in the denominator, so I'm going to multiply everything through by x to clear that. And when I look on the other side, I have a 6 in the denominator, so I'm going to multiply everything through by 6x. So as I distribute to all 3 parts, here's what we get. So 6x times x is 6x squared. 6x times 2 over x, I know that those x's would cancel, and I would be left with just 6 times 2, which is 12. And then in the next case, the 6's cancel. When I'm going onto the other side of the equal sign here, the 6's will cancel out, and so I am left with 73x. So again, multiplying everything through by all of the denominators gets rid of all of our fractions, and it turns something rational into just a polynomial that we certainly know how to solve. So with any other quadratic, as I would do with any other quadratic, I'm going to get 0 on one side. I'm going to put my equation in standard form. Then I'll factor this. So you could use the AC method to factor this. You could use some guess and check. What we end up getting here are 2 options for x. From the first factor, it tells me 1/6, and from the second, it tells me 12. So when I get my 2 answers, I want to do a couple things. I want to look and see, are any of those extraneous? Do they make the original equation undefined? And in this case, neither one does. The only thing that would make the original equation undefined is 0 because of that x in the denominator. But the other thing I'm going to look at, as well as looking out for extraneous solutions, is what did the problem tell me x had to be? So when we reread the problem, it says the sum of a whole number and twice its reciprocal. So that tells us we know that x can only be 12 because that's the only whole number of those 2. So 1/6 also works in terms of kind of the numeric outcome, but it's not a whole number, so that doesn't satisfy what the problem asked us to find. The next set of examples are actually a little bit easier than the first because we don't have to set up the equations. We can just go ahead and solve them. So as I said, we're going to use that same strategy of clearing the fractions that we were just looking at. So I'm going to multiply all 3 parts of this by each of the denominators. Similar, again, to the last one, I have a denominator of 1, so I can kind of ignore that. But I know I need to multiply through by x minus 2 and x plus 2. Now, when I do this and I'm looking at these first the first fraction within my parentheses, the setup of the original problem, times the two things I need to multiply through to clear the fractions, I know that the x minus 2's are going to cancel from there. So I would just be left with the x plus 2 times 1, which is just x plus 2, but I'm going to go ahead and write it out. Then I have my plus sign, so we already did this one. Now we're going to the next term. So nothing's going to cancel there because of the 1 in the denominator. So I have 2, and then x minus 2, x plus 2. Then we have our equal sign, so now we're going to distribute to this last part. And in this case, the x plus 2's are what will cancel. So we have our 3x from our numerator and then x minus 2 in the denominator. And what's left to do next is just start multiplying, combining like terms, same as last time, get 0 on one side, factor, solve, check for extraneous solutions. So it's not as bad as it sounds. 1 times x plus 2 is just x plus 2. If I FOIL out these values, I'll get x squared minus 4, because that's like the difference of squares. And then I need to multiply it by this 2. So I have 2x squared minus 8. Then distributing the 3x into these two terms, we have 3x squared minus 6x. I'm going to get everything on one side. I'm actually going to move everything over. I think I'm going to move it over here because I like to keep the x squared terms positive. So if I subtract this 2x over here, I will accomplish that. So I've got 0 on this side. I'm going to have x squared. I'm going to move this x over to get negative 7x. And when I combine this positive 2 and the negative 8 on this side, I get negative 6. Adding it to the other side is plus 6. So I'm left with this quadratic. Pretty easy to factor. I get my two solutions. I look back at the original problem to see if either of those make a denominator 0. And since they do not, both are good, and I'm done. What makes this next example a little bit different is two things. One, we don't have anything going on the other side of the equal sign except for just a number, and that number happens to be 0 here. Two, we actually have a quadratic in one of the denominators. And if that were to happen on any problem, a quadratic, a cubic, anything besides something linear, then we're going to want to factor that first to make sure we grab everything we need in order to clear the fractions when we multiply through. So x squared plus 2x factors to x and x plus 2. When I'm looking at what all of my denominators are, actually the x and the x plus 2 are already represented elsewhere. So I just need to multiply through by those two things. And so it's not that that wasn't helpful to do that factoring. That factoring actually let us know that we didn't need to multiply through by x squared plus 2x in addition because it's already captured here and here. So that was an important step. All right, so let's continue on and see kind of what cancels out and what doesn't. So I'm looking at taking these two things times my first term. The x in the denominator will cancel with the x that I'm multiplying through. So I will have my x minus 3 and then the x plus 2 left over. Then I have my plus sign. So now we're going to the next term, and in this case the x plus 2 cancels. So we have the 3 from the numerator and the x that we are distributing. And then to our next term, both will cancel, so we're just left with 6. And we can't forget about what's going on the other side of the equal sign. It's kind of nice that it's a 0 because 0 times anything is just going to be 0. So just like before, we'll start to simplify. So we get x squared minus x minus 6 when we FOIL those out. Combine like terms. We've got x squared, let's see, plus 2x, and then the 6's cancel. We can just do a greatest common factor here. And we get x equals 0 and x equals -2. Before we just kind of circle those answers, we are always checking for anything to be extraneous. Because we have 0 here and just x in the denominator, that tells us that that 0 is going to be extraneous because it makes the original equation undefined. And same thing happens with the -2 actually, because that's going to make this part 0. So what kind of happens here is both are extraneous. And that means there are no solutions to this equation. A way to think about this one graphically, and you guys can check this in your graphing calculators, is if you were to type this entire thing into a y equals and look at the graph, it'll never touch the x-axis. It has no zeros. It has no x-intercepts. So if you're ever unsure about a problem, you can always check that way as well. To wrap things up here, we're just going to do a little bit more trig. And these are very similar to problems that we actually did in our last lesson. It's just designed to give you guys a little bit more practice. So to start, you'll notice up at the top of the screen here, I wrote out the equation for the asymptotes for just the regular tangent function, the parent function without any transformations. And I did the same thing for cotangent, because this problem asks us to write asymptotes for a tangent and a cotangent function that have been transformed a little bit. So thinking about asymptotes and what does and does not matter, we know that shifting our graph up 1 doesn't really matter for the asymptotes, and this -2 in front of the equation doesn't really do anything for us either. It does reflect the graph and it stretches it a little bit, but since we're not assessing any limits here, we're just talking about the asymptotes themselves, that's not going to have an impact on our answer. So what will is this pi over 2 in front of the x. We know that that changes the period of our function. So we can take our original equation, the pi over 2 plus pi n, and think about dividing that, every piece of that, by our pi over 2, and that's going to give us our new equation. So pi over 2 over pi over 2 is just going to be 1. When we take this next piece, the pi's will cancel, and it's like we're dividing by 1/2, which is the same thing as multiplying by 2. And then the end's just going to stay the same. So this is the new equation for our asymptotes of this transformed tangent graph. In the next one, we'll do something similar. We have some pieces that don't matter, so moving the graph down 3 isn't going to have an impact on the asymptotes. However, we have a horizontal shift, and since we're talking about vertical asymptotes, when we move horizontally, that shifts where they are. So there's no period change here, but there is that shift. So I'm actually going to write the original equation of the cotangent asymptotes like this. This is how we kind of construct it when we look at the graph, right? We think about where is the first non-negative, it's at 0, and then what's the distance it takes to get to the next one. That's how we come up with the pi n. So what I'm going to do now is think about moving right pi over 4, so adding pi over 4 to my starting point, and that's going to give me my new equation. I'm not going to mess with this pi n because that is just talking about the distance we travel to get to the next one. And this transformation, right pi over 4, moves everything to the right pi over 4. It doesn't change the distance between the asymptotes. So I get pi over 4 plus pi n. And that's my final answer.